So, hi everyone. So today we will start our tutorial 8. So for today's class, we will continue our discussion upon uh, vibrational partition function, and after that we will start discussing on the last type of partition function, last contribution to the partition function, that is the vibrational partition function. Okay. So. So before starting that, let me just briefly discuss the things that we have learned like in our previous tutorial. Okay. So tutorial 8. So let me just give you a brief recap. So we started our discussion uh, in the last class from the rotational partition function, right? So the rotational partition function, the rotational partition function is like this. These are the different rotational energy levels. The energy scales of this rotational partition function comes after the translational partition function. Then comes the vibrational, and at the last comes the electronic, right? So these are the different energy levels: equal to 0, equal to 1, 2, 3, like that, so on. These are the different rotational levels, energy levels, and the energy of a j energy state is given by Ej equal to hcb j into j plus 1, where j is the energy level, b is the rotational constant. The value of b actually is already established. It's like h squared by 4 pi c pi 6. Then the rotational partition function is given by, if these are the energy levels, simple, we just have to use the conventional form of the partition function. Ur is simply Gz into to the power beta Ej, right? Summation over j. Now for each level, uh, each rotational rotational energy levels is associated with a degeneracy, and the degeneracy factor is given by 2j plus 1. Okay. And the energy Ej is already given, that is hc beta into j plus 1. So that means e to the power beta Ej should be the power beta hcb j into j plus 1. This is the rotational partition function. Okay. So now if the energy levels are very close to each other, then you can treat this thing as a continuous function, right? You can just simply do an integration rather than doing the summation. You can just do the integration, and this will gives you the rotational partition function expression, QR. So we got the expression of the rotational partition function. Next, so now after that, we have basically simplified this whole thing, and we have established that if the temperature, experimental temperature, that is basically denoted here by the T that comes in the beta factor. Okay. In the experimental temperature, that is T, is higher, then we have established the QR takes the form of 1 by beta HCB, right? So here also have defined a new quantity which is known as theta r, that is the rotational, what is this called, rotational temperature. Okay, so rotational temperature you have defined it like HCB by K. This is known as a rotational temperature. Okay, so here QR is simply beta is 1 by KBT. So KBT will become up HCB. So it will be T by HCB by KB. So T by theta r. Okay. This is the expression of the rotational partition function QR. Okay. And this is only valid when the temperature is much higher than the rotational temperature theta r. So now, so this is basically the expression of the rotational partition function. Now, in our last lecture, we have discussed that for let's suppose for depending upon whether the molecule is heteronucleus or homonucleus, there is a function associated with the rotational. There is a factor associated with the rotational partition function, right? That factor is denoted by sigma. So what happens here in the sigma is sigma equal to 1 for heteronuclear diatomic molecule, and sigma equal to become 2 for homonuclear. Okay. Homonuclear means like O2, N2. Heteronuclear means NO, CO, where the two atoms that belongs from two different species in a molecule. Okay. So that molecule is basically a heteronuclear molecule. Now, so based on that, we have solved some problem, right? Next, this is the case for the linear system. Okay, like where the system looks like this. So there are two atoms which kind of connected with a rigid rod kind of a thing. Okay, and because of that, this mass of M1, M2. So this is a typical example of a diatomic molecule, linear diatomic molecule. So for this kind of molecular systems, we have calculated so far the rotational partition function QR. Now, for the non-linear molecules, okay. So for the case of non-linear molecules, uh, the expression of QR would be change a bit. Okay. So the QR would then become one by sigma Kt by Hc to the power 3 by 2 by pi into ABC to the power half. So here the new things that comes first, that is the introduction of three constants which are A, B, C. So here instead of 1 in the case of linear molecules, here we are using three rotational constant, right? A, B, and C. So these are basically the rotational constants. Okay. So here there is no mathematical expression that is defined for these constants, right? So these constants actually you have to measure experimentally for different types of molecule that your study of interest has different value of ABC. Okay, so you have to do experiment with the molecule to get the value of this rotational constant. Okay, so should be measured by experimental. Okay, so now next so now in the second case what we have done, so we have solved some problem regarding this, like for the case of heteronuclear and homonuclear case. Like in the case of non-linear molecules, where the molecules are heteronuclear, homonuclear. So we have solved some problems, like our temperature, particular temperature is given, which is basically higher than the rotational temperature theta. So for that case, if we know these rotational constant values, how can we, how what will be the how to calculate the rotational partition function? So based upon that, we have done some problems. Next that we have discussed, that is the vibrational contribution to the partition function, right? So, so a non-linear molecule, let's suppose a non-linear molecule consists of n atoms. In that case, the number of modes of vibration is would be 3n minus 6, and for linear molecule of n atoms, the modes of vibration would be 3n minus 5. Okay. So this is the modes of vibration. So actually, this vibrational partition function is depends upon the total number of modes of vibration. Okay. So basically, the expression of the vibrational partition function QB can be written like this: QV1, QV2, up to the number of the vibrational total number of modes. So if there are kth modes are there, so then the multiplication would reach up to QVK. Okay. For kth normal modes of vibration. So QV, the expression of QV would be looking like this for the case of a normal mode of rotation for an atomic molecule. Now, uh, so regarding that, we have solved some problems, like if the suppose a molecule non-linear, the molecule that consists 10 atoms or 20 atoms, then how the expression of the vibrational partition function looks like. Next, what we have discussed, we have considered the vibrational. We have considered the vibrational excitation uh, as a harmonic oscillator. Okay, so the vibrational frequency basically matches with the frequency of a harmonic oscillator. So basically, we've ignored the anharmonicity term of the vibrational energy. So what we have done, approximated the vibrational excitation with harmonic oscillator. So we have done that, and we have used the expression of energy EV equal to, or E nu something, anything E nu, let's suppose E nu equal to nu plus half h dot c nu tilde. Nu tilde is the frequency. Okay, the nu value is varied from 0, 1, 2 like that. So this is basically the expression of the vibrational energy states we have considered for the case of by approximating the vibrational excited state as harmonic oscillator. Okay. So by doing that, we have calculated the vibrational partition function that is denoted by QV. QV simply Gj into e to the power beta Ej, right? So here there is nothing, there is no degeneracy associated with the vibrational energy level. So Gj will simply become 1. That means E equal to minus b to the power mu plus half into hc nu theta. The summation would be over nu. Now here now what we done next, that we have actually input the 0-point energy. Okay, so if you input the 0-point energy into the expression of the energy, then this would be become, this whole expression would become e to the power minus beta hc nu tilde. So that means QV would be summation over nu e to the power minus beta hc nu tilde to the power nu, right? Nu, the summation will be from nu 0 to infinite. So now after that, so this basically gives you an infinite geometric series, right? Now if you do the sum of this infinite geometric series, this would basically gives you QV equal to 1 plus e to the power minus beta hc nu tilde plus e to the power minus 2 beta hc nu tilde, like this. So at the end, QV would be looks like 1 by 1 minus beta hc nu tilde. Okay. This is the expression of the vibrational partition function that we have discussed. Next, a similar way for the case of rotational. Here also we have considered two cases. One is the high temperature case and one is the low temperature case. So for the high temperature case, so for let's take for low temperature first. Okay, low temperature case. So that means KT would be smaller than hc nu bar. So that means beta by hc nu bar would be smaller, would be greater than 1. Greater than 1. So that means that, so QV's expression is given by this. QV is 1 by 1 minus e to the power beta hc nu tilde. This thing becomes very high. So 1 by infinite, so that gives you 0. So 1 by 1 QV, so it's approximately become 1. Now for high temperature case, that means 1 KT would be greater than hc nu tilde. In that case, beta hc nu tilde would be greater than 1. So that means QV becomes what would be the expression of QV? Okay, so QV now becomes 1 by 1 minus e to the power beta hc nu tilde. So QV, now if you expand this whole things, uh, the summation, like you can write this exponential term as a summation, right? There's a minus, okay. So if you do that, HC nu tilde and other higher terms, just neglect, because HC nu tilde is much smaller than KVT, right? So that means, so basically beta into HC nu tilde is much smaller than 1. So we can take up to first order, we can ignore the higher order terms. In that case, QV would simply become 1 by beta HC nu tilde, or KT by HC nu tilde. Now here also, just like the case of rotational partition function, here also we have defined a temperature, a characteristics temperature, which is known as the vibrational temperature. So the expression of the vibrational temperature, we have written it theta V. Theta V is simply HC nu tilde by Q. Okay, so QV you can write as T by theta V. Theta V is the vibrational temperature. Okay, so that means when the temperature of the experiments is higher than the vibrational temperature, much higher, then we can use this expression simply. And if it's very low compared to the case of characteristic vibrational temperature, the experimental temperature, then we will simply get QV almost close to 1. So these are the two extreme cases that we have discussed for vibrational partition function. Now what we will be looking to through some example, how for the case of different temperature, one case would be we'll be simply taking high temperature, and one case will be taking low temperature, and we will see how this expression of the QV or the vibrational partition function will vary. Okay. So the problem number 1 is, so let's do the problems. So the problem 1 is the 3 fundamental vibrational wave numbers of H2S are nu 1 as 2615 centimeter inverse, nu 2 tilde is 1183 centimeter inverse, and nu 3 tilde is 2626 centimeter inverse. Okay. So these three are basically the vibrational wave numbers. Now, so now given that three fundamental vibrational wave numbers of H2S, now in the next case we will evaluate the vibrational partition function QV. The question is, evaluate the vibrational partition function QV at t equal to 1200 K. Okay. So the other parameters are given in the problem. H value, not H cut. Planck's constant. H value is given 6.623 into 10 to the power minus 34 joule second. K value is a Boltzmann constant value is given 1.381 into 10 to the power minus 23 joule per Kelvin. C is given 3 into 10 to the power 10 centimeter by second. Okay. These are the supplied constant values. Okay. So now, so we know the expression of vibrational partition function QV is this. There are three sets of, for a set, there are three independent modes, right? One is QV1, QV2, and QV3. Okay, so you know QV is the summation over QV1, QV2, and QV3. Three independent modes are there. So QV would be simply the multiplication of all the three independent modes. So now the expression of QV is given by this 1 by 1 minus exponential HC nu tilde by KT, right? Now the first thing what we will do is that we will check the characteristic vibrational temperature for all the three cases, and we will check whether the temperature that is supplied here in the problem is higher than the vibrational temperature, or it's lower than the vibrational temperature, right? So because then it would be easier for us to implement the simplified formula, so that our calculation becomes much more easy, right? So the expression of theta v looks like this, right? Theta v is simply Hc nu tilde by K, Boltzmann constant. So there are three thetas are there. So theta v1 is H is, we already know, 6.623 into 10 to the power minus 34. C no is the speed of light, 3 into 10 to the power 10. We are using in SI unit, so sorry, SI, yeah, so centimeter unit basically. So this is because in the problems frequencies, wave numbers are given in terms of centimeter inverse, right? So wave numbers here is the 2615. First case, it's divided by the K. K is 1.38 into 10 to the power minus 23. Now if we do the multiplication first, we have to multiply the numerator 6.623 into 10 to the power minus 34 into 3 into 10 to the power 10 speed of light into 2615. Now if you do the multiplication, you will be getting 3.762 into 10 to the power 3 Kelvin. Okay, so this is the first vibrational characteristics temperature. So from the question itself you can see this theta v, T is this, T is 1200 Kelvin. So for the first vibrational temperature, for the first case, vibrational temperature is higher than T, right? So we cannot simply use this simplified formula, right? This one. Okay. So we have to use a normal conventional formula actually. Okay. So next case, what you have to do for that for the second case, right? Theta v2. Theta v2. So the theta v2 same 6.623 into 10 to the minus 34. Speed of light is 3 into 10 to the power 10. And the wave number of light is 1183. 1183. The whole thing is divided by 1.38 into 10 to the power minus 23. If you do the calculation, it will give you 1.702 into 10 to the power 3 Kelvin. Okay. So here also you can see the temperature is actually higher than the experimental temperature, 1200 K, right? It's around 1700 Kelvin, right? So it's quite higher than the temperature of the experimental case, right? So theta v2 also is higher. So for the that means for the second mode also we have to use the same formula which is given by this QV, right? Now we will move to the third one, QV3. So QV3 we will check. QV3 is Similar way, 6.623 into 10 to the power minus 34 into 3 into 10 to the power 10 into, so for the third one the wave number is 2626. Okay, 2626, whole thing is divided by 1.38 into 10 to the power minus 23. This gives you also, if you multiply this 6.623 into 10 to the power minus 34 into 3 into 10 to the power 10 into 2626 into by 1.38 into 10 to the power minus 23. This gives you 3.778 into 10 to the power 3 Kelvin. Okay, so QV1, QV2, QV3, both the cases we have checked. So comparison with experimental. So for all the three cases, T is greater than theta V1, T is also greater than theta V2, and T is also greater than theta V3, right? But all the three cases, the temperature is higher than the vibrational temperature, right? So that means what you can do is simply so for this case we have to use this conventional formula, so we cannot use the simplified formula, we have to use this one, QV1, this one. So so what you can do, so for the first case, so here QV1 first have to calculate. QV1 would be simply 1 by 1 minus exponential to the power minus theta 1 by t, right? So theta 1 you already know, 1 minus exponential theta 1 is 3.762 into by 3, 3.762 into 10 to the power 3. The whole thing is divided by 1200. Okay, now if you calculate the thing, so 1 by 1 minus exponential to the power 3.762 into 10 to the power 3, the whole thing is divided by 1200. So this basically gives you approximately 1.0455 QV1. Now similarly QV2 will give you 1 by 1 minus this whole thing, theta 1 is theta 2 by t. So theta 2 is 1 minus exponential theta 2 is 1.70 to 1.70 to 10 to the power 3, the whole thing is 1200. This gives you approximately 1 by 1 minus exponential to the power 1.702 into 10 to the power 3 divided by 1200. The whole thing gives you this, okay, approximately 1.3195. Now the last is the QV3. One minus the power minus theta 3 by t. This gives you 1 minus exponential. So theta 3 would gives you minus 3.77 into 10 to the power 3 by 1200. If you do this, 1 by 1 minus exponential to the power minus 3.778 into 10 to the power 3. Whole thing is divided by 1200. So this whole thing gives you 1.044. So three contributions are there, QB1, QB2 and QB3, right? So the total partition function Q is simply given by QV equal to QB1 into QB2 into QB3. Now it would be approximately, right, 1.0455 into 1.3195 into 1.0448, right? This will approximately gives you 1.0455 into 1.3195 into 1.0448. So the answer is approximately equal to 1.44. QV is approximately 1. This is like close to 1 basically. The contribution of QV, the partition function QV, is very small, that means, right? The main conclusion is this. So as you can see here in the problem, let me repeat it. So in the problem, for a molecule H2S, this specific molecule, there are three fundamental vibrational modes are given. This can be measured in experiments. These are the vibrational wave numbers basically given, nu1, nu2 and nu3. So we know, as there are three vibrational modes are there, so the total vibrational partition function will be simply the multiplication of the three partition function QV1, QV2 and QV3, right? So now the next thing what we have done, we have written the the expression of the partition function QV, where theta v is simply given by this. Theta v is simply hc mu Tj by k, the expression of theta v, and this is the temperature, the experimental temperature T equal to 1200 K is given. So first thing in this kind of problem that you have to do actually is to check whether the whether the experimental reference temperature, that is 1200 K here, is mentioned, whether it is higher than the characteristic vibrational temperature or it's lower. And depending upon that, our calculation, the way of our calculation can vary. Okay, so to check that, so we have calculated the theta v for all the three modes QV1, QV2 and QV3, and this is the values of the three modes of vibration we got. So and we have compared with the experimental temperature, and what we have find out that for all the three cases the temperature is basically higher than the vibrational temperature, theta v1, theta v2 and theta v3, right? So that means we cannot just simply use this this reduced formula. Okay, so we have to use the original formula, the mother formula here. So so we have calculated QV1 first by simply substituting the rotational temperature values that we have calculated early and the temperature, the experimental temperature, and by doing so we got the expression of QV1, which is approximately equal to 1. Basically, the more high the vibrational temperature is, the more close the QV gets to 1 actually. Like here you can see for QV2 case, the theta 2 you can see is the value of theta 2 is least compared to the other two, right? So for that you can see QV2 has significant contribution compared to the other two cases, while it's almost close to 1 for the other two cases, but QV2 has a bit higher value than 1 because the temperature is a bit closer to the experimental temperature. Okay, so anyway, so we have calculated QV1, QV2 and QV3, and you multiply the whole three things. So after doing that, you got the total vibrational partition function, that is simply a numerical value of 1.44, right? So now next what we will do, similar type of a second problem we will do. Okay, So problem 2, second problem. The problem is defined like this. Uh, Let me write it first. Uh, Non-linear triatomic molecule. Okay, triatomic molecule has 3 vibrational wave numbers. Okay, the wave numbers are basically given. Nu tilde 1 200 centimeter inverse, nu tilde 2 is 300 centimeter inverse, nu tilde 3 is 400 centimeter inverse. Okay, so these 3 wave numbers are given. Now we have to calculate the vibrational partition function UV at temperature T equal to 1000 Kelvin. Okay. Now, so three vibrational wave numbers are given basically. So you have to calculate the total vibrational partition function QV at equal to 1000 Kelvin. So for that, use this thing. So H is 6.623 into 10 to the power minus 34 joule per second. Joule second, sorry, not joule per second, joule second. K is the Boltzmann constant, that is 1.38 into 10 to the power minus 23 Kelvin, joule per Kelvin. And the constant, the speed of light, 3.0 into 10 to the power 10 centimeter per second. Okay, these 3 constants values are basically mentioned in the problem. Now for the 2 cases, for high temperature and for the case for the case of high temperature or low temperature, that you have to first verify whether this problem has high temperature or low temperature. So we would use the similar tactics, right, how like we have done for the previous case. So the expression is given is like this, QV simply. So let me first write the QV, the expression of QV. Similar here also, QV would be the multiplication of the 3 modes, QV1 into QV2 into QV3, right? So the expression of QV looks like this, QV equal to 1 by 1 minus exponential e to the power 8 to C nu tilde by KT, right? This is the expression of QV. Now here, what you have to do, so the theta V, okay, the vibrational temperature is given by this, theta V is HC nu tilde by K. So the same thing will be followed here also. So first we will calculate the theta V1. So that is basically similar way. Six point 623 into 10 to the power minus 34 into 3.0 10 to the power 10 into 200, right? 200, the voltage is divided by the Boltzmann constant, that is 1.38 into 10 to the power minus 23. If you do the numerics, then this gives you 6.626 into 10 to the power minus 34 into 3.0 into 10 to the power 10 into 200. The whole thing is divided by 1.38 into 10 to the minus 23. So theta V1 gives you 287.74 Kelvin, right? So second is theta V2. So theta V2 is the the vibrational temperature for the second vibrational mode. 6.626 into 10 to the minus 34 into 3.0 into 10 to the power 10 into the second case. It's for the second case. The temperature, the wave number is 300, so 300. The whole thing is divided by 1.28 into 10 to the power minus 23. Now, if you do the calculations, it gives you the 6.626 into the minus 34 into 3.0 into the power 10 into 300 divided by 1.38 into 10 to the minus 23. So this gives you 431.62 Kelvin. Last theta V3, 6.626 into 10 to the power minus 34, 3.0 into 10 to the power 10 into 400, right? Yeah, 400. So 400, the whole thing is divided by 1.38 into 10 to the power minus 23. So if you do the multiplication, 6.626 into 10 to the power minus 34 into 3.0 into 10 to the power 10 into 400, the whole thing is divided by 1.38 into 10 to the power minus 23. If you do the calculations, it gives you around 575.449 Kelvin. Okay, these are basically the approximated values of theta V. So if you compare it right now, the temperature is mentioned, experimental temperature is 1000 Kelvin, right? So T is the 1000 Kelvin here. T is 1000 Kelvin. So as you can see, if you compare with the comparison of temperatures, you can see for all the three cases, the temperature is greater than theta V1, the temperature is greater than also theta V2, and the temperature is also greater than theta V3, right? For the whole three cases, the temperature of the experiment is higher than three modes of vibrational temperature, right? So that means we can approximate the formula, right? This to this theta V, you can write the approximate formula is T by theta V, right? The vibration, these are vibration temperature, right? So therefore this is the higher temperature case, we can use this approximate formula here. So by using that approximate formula, for the three cases, for the QV1 cases, QV1, QV2, QV3, you have to calculate. And QV1, T is 1000, you know. Theta V1 would be 287.74. 287.74. If you divided these two, so 1000 divided by 287.74, it gives you almost 3.475. You can see QV2, if you do the same way, 1000 divided by 431.62, 431.62. If you do the calculation, it gives you 2.316. Last one, QV3, 1000 divided by 575.49, 575.49. If you do the calculation here also, it would simply gives you T is 1000 divided by 575.49. So it gives you 1.73, 1.737, right? So QV1, QV2 and QV3 value we got. So the total QV value would be simply the multiplication of all the three, QV1 into QV2 into QV3, right? So this gives you basically 3.475 into 2.316, 2.316 into 1.737. So if you multiply these three, this gives you 13.99 QV. So as you can see, For this case, what temperature you can see is much higher than all the three vibrational characteristics temperature. The QVs, the vibrational contribution to the partition function is significantly large, right? You can see for all the three cases. So that means that temperatures actually do affect a lot of things that is related to the vibration in a molecular system. So for the first case, where you can see the temperature is lower than the vibrational temperature, we use a normal formula of the vibrational partition function. The temperature is lower basically from, sorry, this should be smaller than smaller. Here it's higher, right? Yeah, here it's higher. Okay, so there's a mistake. So this is should be a smaller than sign, not the greater than. So anyway, so when the temperature is smaller in compared to the vibrational characteristics temperature, simply we got QV1, QV2 and QV3, and their values are almost equal to 1. So by multiplication got the value QV equal to 1.4, very close to 1. Next case the temperature is higher, so we got the expression QV is 13.9, right? So next, so this is done right now. So next we will start about some discussion about the electronic contribution. Okay, so far what we have discussed, the rotational translation we have discussed first, then rotational, and the last we have discussed the vibrational case. Now we will discuss about the electronic contribution. Okay, so electronic contribution. Okay. So actually what happens, the electronic contributions, so compared to the rotational, vibrational or translational case, for the electronic case the energy levels are very actually large. So gradually what comes that the system in most of the cases, unless the temperature is very high, the system mainly remains on the ground state of the electronic energy states, right? Most of the cases, unless the temperature is very high, because the energy, the difference between the energy levels are too much actually in the case of electronic what you can say, energy levels. Okay. So so what happens, let to write it. Electronic energy levels separation is very high. So like if these are the energy state, 0, E1, E2, E3, E4, like this energy difference between 0, E1, 0, E2 is delta E, that is actually very high. For the case of vibrational energy levels, right? So sorry, electronic energy levels. Okay, so unless the temperature is not very large, the vibrational energy is like there is a contribution of electronic is very low, as the system tends to remain in the ground state. Okay, anyway, so we'll see what happens. So first thing is just write the vibrational, what do you say, electronic partition function. Similar way, the general expression from the general expression of the partition function you can write this thing basically. So Q is the electronic partition function. Is basically is on the energy states J, Gj into e to the power beta Ej. Okay, Ej is basically the energies of different states of vibrational states, right? So if you do the summation, it gives you QE, the electronic contribution is simply G0 plus G1 e to the power beta E1 minus beta E1 plus G to the power minus beta E2. So like so on, it goes on. Now for the case where, as I've discussed, so as energy levels are very high, so what we generally do, we generally involve the ground state or max to max, the first excited state of state in the partition function contribution of I. Okay, so that means we will only consider the first ground state, that is a G0. So ground states, for the case of ground state, only the degeneracy factor will be, we have to only consider the degeneracy value, right? If system remains in its ground state, right? So for the case of electronic case, the QV simply would be approximately G0, or it can be, we can take the first excited state also for certain cases, that is G0 plus G1 e to the power minus beta E1. So that is most likely the approximated partition function you can take for the case of electronic contribution, right? So so now we'll check how the partition function basically looks like if you change the temperature. So okay, so let's take this expression Q equal to G0 plus G1 e to the power minus beta E1 of V. So now take G0 as 2 and G1 as 2. So that means both the state, the ground state as well as the first excited state, has two degeneracy associated with it, right? So the total partition function, electronic contribution, takes the form 2 plus 2 into 2 to the power beta minus C. The energy, let's suppose for the time being, is E, only E, EI is E, so only we're taking the E1 as E. So now, so we'll take, so in order to get the curve, qualitatively get the curve, we will check at to limiting temperatures how this function looks like. So we will first take T tends to 0. At T tends to 0, this Q to the power minus beta epsilon also tends to infinite, right? So that means sorry, this plus part tends to infinite, yeah. KBT, yeah. So Q, so this part basically becomes 0, that means, okay, tends to 0. That means QV would be simply equal to 2, right? And when the t terms tends to infinite, okay, then e to the power minus beta e, this term tends to 1 because beta by e also tends to 0, right? So that means q to the power beta e would tends to 1, so qv would becomes 4. Okay. So if you plot the function, it would be looks like this. Let me try it carefully. This is 4. This is 2. Okay. This is QE. This is the KT by epsilon, the temperature. Okay. So this is how it looks like. How the basically the electronic contribution to the electronic partition function looks like by varying the temperature. Okay. Okay. So that's it. Okay. So next what we will do? Next we will write all the contributions from rotation, translation of rotation and vibration electronic case. Okay. So we will write that. Okay. So okay. The overall partition function Q looks like Q translational multiplied by rotational multiplied by Q vibrational multiplied by Q electronic, right? 4 contributions are there. So, uh, so how does it look? So translational it took, we know it looks like this. Like we trapped a gas molecule, a non-interacting gas molecule inside a 3D box, and from that problem we actually derived the expression of translational partition function, right? That for 3D system this looks like this. P by lambda cube, right? When lambda is a thermal wavelength, and V is the volume of the enclosure. Okay. Translational. QR is the rotational. So for the rotational case, the expression is given by this. So the expression is given by K by sigma theta r, right? Where theta r is basically HCB by K, and this expression is only valid when T is greater than theta r, right? So this is the expression of T expression for the case of rotational case, right? Uh, yeah. The vibrational case, for the vibrational case, it will be looks like this: 1 minus alpha beta hc mu tilde, right? This is the vibrational case. So rotation, translation, and vibration. Three things are defined here already. So now G is the electronic contribution. So electronic contribution is the part. So so as you know, all the three contributions, the electronic part we will discuss later. Okay. So first thing, the electronic contribution is already actually done here. So we have only take like Q we can be simply take as just the degeneracy of the first ground state, right? Q is simply like that you can take um, for a wide range of temperature, right? Unless the temperature is very high, the electronic state simply remains so at ground state only, right? So QU you can simply write equal to the degeneracy of ground state, that is represented by G0. So so what you can do now, you can, for a molecule, let's suppose all the four contributions are there. For that case, first we will calculate the mean energy of the molecule. Okay. So uh, so the mean energy of the molecule can be written as evaluating sums simply for each atom. Okay. So for each, sorry, for each contribution. Basically, the thing is the total mean energy of the molecule will be the sum of sum of the mean energy of each contribution. So first, what we will do, so the first we will first calculate the mean translational energy of it. So the mean So we know the expression, like the from thermodynamics statistical mechanics point of view also, we know the expression of mean energy, that is given by mean energy minus q del beta at constant volume, right? uh, so now for the translational case, it would be et. T simply denotes translational, so et average would be simply 1 by qt by delta qt by del beta, right? Now q translational is simply x by lambda. Okay. For the time being, here we are only considering the 1D case. Okay. So lambda is, you already know, lambda is the thermal wavelength. That expression is given by basically beta h square by 2 pi m whole to the power half, right? Now, now if you do the calculation, et is simply uh, so it's x by sorry qt, so v lambda will become the numerator, x come at denominator, del beta of x by v, so x by lambda, sorry, it's not v, it's lambda, so it would now become, you know, lambda is a function of beta, right? So how, what you can do, you can take it lambda by x outside, x is also come outside. So if you do the derivative of 1 by lambda with respect to beta, so it first gives you minus 1 by lambda square into delta lambda delta beta, since lambda is a function of beta, as you can see here. So now et, second step, what you can do, you can cut this thing, so only the lambda will retain, right? Lambda square, so lambda will retain, sorry, 1 by lambda will retain. There's a 2 factors also there. Okay, so 1 by lambda del beta is simply gives you del beta of beta a square 2 pi m to the power half. If we do the derivative, half will come outside, 1 by 2 lambda. Beta is there, so beta is simply derivative, beta go out 2 pi m, and if you put the lambda here, so if you now express the value of lambda, so now 1 by 2 pi m beta h square half by h square 2 pi m the minus half. So now 1 by 2 beta, so lambda 1 by lambda by lambda, the lambda will cancel, so half by kbt, right? Et, the expression of et would be half into kbt, right? Okay, so this is the expression of the what is this called, uh, translational energy, mean translational energy, right? So as you got the mean translational energy, next thing that we can find is the so for 3-dimensional, you know, this is for the case of 2-dimensional. So for 3D, we know there's a simply 3 factor will be multiplied in here. So for the case, for the 3D case, et would be simply 3 by 2 kbt, right? So anyway, and this basically match with our classical result of mean translational energy that comes from the kinetic theory of gases, and that also gives you 3 by 2 kbt for the case of 3D gas, right? Now comes the mean rotational energy. Okay, so for the case of rotational energy, okay, so rotational energy, Um, would be looks like this. QR is um, mean rotational energy. Okay. So for mean rotational energy, so first let's check how the rotational partition function looks like. Rotational partition function Q are simply given by this j equal to 0 to infinite j plus 1 into bar beta hc bj into j plus 1, right? Now for j to vary, j starts from 0, 1, 2, 3. So QR would be starts from 1 plus 3 into to the power minus 2 beta hcb plus 5 into to the power minus 6 beta hcb and so on. The QR looks like this. If we do the summation over j, now now by acquiring the expression of QR, next we will do the calculation of mean energy that comes for the rotational contribution. So ER is simply 1 by minus 1 by QR into delta QR by delta beta, right? Now here, so QR you already know here. So if you substitute the QR expression here into the expression of ER, that gives you, the ER basically gives you, if you do the derivative, so ER gives you the okay, so in the denominator part, so let me write it, 1 plus 3 into to the power minus 2 beta hcb plus 5 into the power minus 6 beta hcb and so on. This is the QR part. And if you do the derivative of del QR del beta, the first term would be 0. The next term it will come 3 into 2, so it would give you 6, right? So then a minus sign would also be there. So minus 6 hc b into e to the power minus 2 beta hcb. Again it would be, so again it would be a minus, so minus 6 into 5 30 hcb into e to the power minus 6 beta hcb. So like so on, there's a minus sign in the forward also. So it goes on like this. So the minus sign will absorb, you can absorb the minus sign, right? So so after doing that, the expression simplifies into then like this. You can take hcb as common, this factor. So 6 into e to the power minus 2 beta hcb plus 30 into e to the power minus 6 beta hcb dot 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 dot. This whole thing is divided by 6 beta hcb. So as we got the average rotational energy, right? Now the thing is that uh, okay, yeah. So now what we can do here from there, we can approximate the thing for the case of linear motor, right? Linear rotor, sorry, linear rotor. So for the case of linear rotor, and for the case if t is greater than equal to theta, that is the characteristics rotational temperature. So for that case, we know already QR is 1 by sigma HCB, or you can write simply as T by theta, right? Theta is the rotation temperature. So for that case, this expression of ER becomes much more simpler, right? QR by del QR by del beta. If we do that, it's very simple. If we do the derivative with respect to QR, so beta is there, sigma HC, this a beta is there, so 1 by, so this is, so it will become HC B beta, beta is there, so minus 1 by beta square into 1 by sigma HC B. So it's sigma HC will cancel, so it gives minus 1 will absorb, so it will gives you 1 by beta epsilon r. Okay, equal to 1 by beta. So now, so ER is simply, that means for the case of, so for normal temperature case is this for and for high temperature case, the ER is simply KBT. Okay, KBT, K is a Boltzmann constant for the high temperature case. Okay. Anyway, and for non-linear rotor, that means for 3D case, non-linear rotor, that means for 3D case, the ER would simply, the rotational part is 3 by KT. If you can do, you can check it actually. Now comes the vibrational part. Okay. So mean vibrational energy, the same way we have to do it here also. So EV is basically given here by EV is 1 by QV, that is into del QV by del beta at constant volume. Now QV is given by 1 by 1 minus e to the power minus beta HCB. Okay, so now what you have to do, so first do the derivative. So if you do the derivative with respect to the QV, so del beta of QV is nothing but 1 by 1 minus the power beta HCB. So for doing that, we'll be getting a minus sign up front, so 1 minus 1 by BHC nu tilde. Nu tilde is nothing but just that that wave number, so that is minus 1. Now in the denominator, 1 minus e to the power minus beta HC nu tilde square term would come, it, and the whole thing is into minus e to the power beta HC nu tilde, right? Yeah, and minus HC nu tilde, yeah, this is it. So okay, after substituting this, you will be getting this. Now this is basically the average image. Now if you just cut the common terms, then the EV would takes the form HC nu tilde into e to the power beta HC nu tilde to the divided by 1 minus e beta HC nu tilde, right? Now here, so you can make this expression more simpler, right, by dividing the numerator and denominator by e to the power beta HC nu tilde, right? So the whole thing become HC nu tilde divided by e to the power beta HC nu tilde minus 1. This is the expression of the mean free energy, right? Now Here also you can take the same approach here also. Okay. Um, okay. So what you can do here? Let's take the case like this is the case of normal temperature. So here also you can consider the fact for high temperature, right? Where the T is much higher than the HC number. So let me do it here also. So let's take the case where for the case of high temperature. High temperature means what do I mean? KBT temperature is higher than, or you can take the rotation, the reference, the T is much more higher than the theta V, right? So theta V is nothing but HCB HC, so HCIK. I'm saying it, just take the expression of theta V, we forgot one second, theta V is HC nu tilde is also right. So HC nu tilde plus K, right? So that means KT is will be greater than HC nu tilde, right? So that means we can further EV, we can split this exponential term into a series term, right? So 1 plus e to the power, so after splitting this term, this exponential term, we can write up to the first order. As you know, you can safely neglect the higher order terms. After doing that, we will be getting the vibrational part as HC nu tilde by beta HC nu tilde. So nu tilde will cancel upon, and we'll be getting beta is simply HC is also cancel. So you will be also getting here KBT, right? Okay. So that means for the vibrational part at high temperature case also, the contribution is simply the KBT. So similar the rotational case also you got KBT. Here also you got KBT. So for two cases you got KBT. The last comes the electronic part. So we'll check the electronic part. So now comes the mean electronic energy. This would be much more simple because there are nothing much more, like nothing complicated terms are there, right? So we know Q is simply given by the J, Gz e to the power beta Ej. Ej are the electronic energy levels. As you know, the energy separation is very high. We have discussed it earlier also. It's very high in electronic levels. So what are the approximation you have taken? We have simply make the electronic partition function is equal to the approximated to the degeneracy of ground state energy levels, right? That is denoted by G0, right? So that means we can write E as the average energy, that comes from the electronic contribution as into this angular bracket here. So here you can write 1 by QE into del QE by del beta at constant volume. So that as G0 is just a constant number, right? So derivative would gives you 0, right? So the mean energy contribution gives you 0 for the electronic contribution, right? So far what we have done is let me just summarize the whole thing here. So our main goal was to, so where it starts, yeah, from yeah. So our main goal was to calculate the mean. So once you got the partition function that comes from for like the for whole thing like the translational, rotational, vibrational, electronic case. Then we actually calculated how the mean energy of the whole molecule is looks like. Okay, like after considering all the four contributions, right? So first we calculated the translational contribution that gives the translational mean energy. So we actually know how to calculate the mean energy if you know the partition function, you know the formula for that, right? So for the translational case, we know the translational partition function Qt, and from there we have calculated the translational energy, the mean translational energy that gives half kBt. We have calculated for 1D case. Similarly for 3D case, the translational energy gives you 3 by 2 kBt. Similarly for mean rotational for the rotational energy, we have calculated the mean rotational energy that gives kBt. Normal kBt, not half factor is not involved here. That is actually the case where the temperature will be higher than the theta, right? If it's normal temperature, then ER takes a form like this, a very complicated type of form, okay, where there's several terms is involved, basically infinite series involved. Okay, but if you take the case where t is greater than theta, then the thing is become much more simplified. It gives you just a kBt value. Now case the vibrational case. Similarly, we have calculated for normal temperature, and for higher temperature the average energy due to the contribution of vibrational part gives you the value kBt. The last comes from the electronic contribution. So electronic contribution, we know the electronic energy states are much more separated from each other. So that means the partition function is equal to only the degeneracy of ground state energy level, right? So QE is the electronic partition function is approximated equal to G0, which is the degeneracy at ground state energy level. So if you calculated the mean energy due to the electronic contribution, that gives you 0 basically. So this is how you can calculate, okay, the mean energy for each of the cases. So now next thing that we will be discussing briefly is about the heat capacity. Okay, so so what happens here? So that is like a bit different thing from the cases that we have discussed so far. Okay, so heat capacity. So let me write the thing, the name of the topic. Heat capacity. Heat capacity. So okay, so the expression of heat capacity for any kind of system, CV, at constant volume. Let's take the heat capacity for constant volume. Looks like this. If you write in terms of a thermodynamic potential, let's suppose internal energy U, it looks like this: del U, del T at constant volume. So the original expression of heat capacity looks like this: dq dt. Okay, that means the heat that is required to the heat, if the dq is the amount of heat that is required to raise the temperature of a substance by an amount dt, then its heat, the specific heat definition is simply dq by dt, right? Now for the case of constant volume, we can write dq as du plus dw, right? So dq is du plus dw, you know, pdv, right? So if volume is constant, so dv is 0, so pdv simply becomes 0. So for the case of constant volume, we can write the specific heat at constant volume as del u by del t at constant v, right? So now we got the CV term here. So now we can simply write d dt as this simplification. The reason for which we are doing this simplification is just to make the calculation a bit easier, right? So you can write d dt, since the all that thermodynamic quantities so far we have write in terms of beta, not explicitly in terms of the temperature, right? So it would be beneficial for us to write the derivative also in terms of beta, not in terms of temperature, right? So you can write this derivative in terms of beta like this. You can write d dt as del beta del t into d by del beta, right? So del beta del t is nothing but beta, kbt, 1 by kbt. So del beta del t is just 1 by k minus 1 by kbt square, right? So it would become minus 1 by kbt square into d by d beta. Okay, so yeah, so whole thing can write is like this. So kbt can multiply 1k on both the sides, so this gives you k beta square d by d beta, right? So cv you can write like this, minus k beta square into del u del beta at constant volume. This is a modified expression of cv, specific heat at constant volume, right? Now the next thing what we'll do, uh, so in order to calculate the specific heat, we have to express we have to write basically the internal energy in terms of the mean energy of the system, right? So internal energy you already know is this. This is the way we write the internal energy minus u0. U0 is basically the 0 point energy. So if you divided it by total number of molecules or the particles, this gives you the mean energy, right? Mean energy is nothing but the energy that we have calculated just now, just previous discussion, like by taking the contribution of rotation, translation, vibration, electronic, that mean energy we are using here also, right? So now since we got the so now CV, that means is simply n into del beta del delta t of whichever format you need, you can write, or it can be equal to, in terms of beta, then k beta square into delta E by delta beta. Okay. So now, um, the specific heat at constant volume, the expression looks like this. Okay, so okay. Now what you can do? Okay, so uh, things are now becomes a bit complicated. Okay, so now uh, so we will now take the contribution, okay, like for translation, rotation, and all the things. Okay, so first we'll take the rotation. So first we'll take only the translation and contribution. Okay. So we will denote it the CVT. Okay, so the specific heat at constant volume comes because of the translational part of the mean energy. Okay, so that means we can write it like this, minus so n delta E at translation by delta T at constant volume by n delta by delta T by 3 by 2 kT at constant volume. So this gives us 3 by 2 K into Na, 3 by 2 R CVT. Okay. The specific heat at constant volume, the translational contribution basically gives you this value 3 by 2 R CVT, right? So this basically is consistent, right? What you have like this whole thing, this specific heat thing, we have actually previously calculated using thermodynamics also, right? Right now we're doing using statistical mechanics, but in the before courses you have done using the thermodynamics, right? From the kinetic theory of gases, basically classical thermodynamics. From there also you got the specific heat value at constant volume, 3 by 2 R, right? And that is the same thing we're getting here also by using the statistical point of view, right? So so the thing is, the whole framework, that means it's consistent with the thermodynamics. That is the whole point. Okay. Now, for ideal cases, we know this formula, right? For ideal gases, the Cp, the relation of Cp/Cv, right? Cp minus Cv is because just NR, right? N is the mole. So for 1 mole, let's suppose N equal to 1. If we know the Cv, you can calculate the Cp from here, right? So Cv we know 3 by 2 R. So from there you can calculate the Cp. That is the R plus 3 by 2 R. So Cp gives you 5 by 2 R, right? 5 by 2 R. So okay. So that's it. So now so now so that means for ideal case, if you know Cp by Cv, you can calculate the R. You can if you know the Cv, from there you can easily calculate the Cp. And for there is also one thing what is denoted by gamma, which is nothing but the ratio of Cp and Cv, which is basically 5 by 3. This gamma is nothing we have learned in the thermodynamics course, right? This gamma is nothing but the adiabatic constant, right? That is for a adiabatic case, adiabatic process, we know the equation of state for an ideal gas looks like this: PV to the power gamma is equal to K. This gamma we know that this is known as basically adiabatic gas constant or gas factor, something like that. That factor expression is given by this actually, gamma equals ratio of Cp by Cv. Okay. Okay, so this is some things for the case, like for some preliminary discussion, basically you can say, about specific heat. Now we'll do some problems. Okay, so first problem we will do. So problem 1 we will do. One mole of an ideal gas, ideal diatomic gas is heated at heated from 300 Kelvin to 400 Kelvin, right? Now you have to find out basically the heat required at constant volume. And the second thing you have to find out the heat required at constant pressure. So these two things you have to basically calculate. Okay. Okay. So the expression of QV. So first thing is the in the question it mentioned that 1 mole of ideal diatomic gas is heated from 300 to 400 Kelvin, right? So CV actually is given actually in the problem. Okay, so CV is 5 by 2R. So for for that case, that means if CV is given in the problem, so the heat required you can easily calculate, right? Because we know QV, the heat that is required, or delta QV, whatever, is simply NCV into delta T, that is the heat that has been raised, right? So, so for that means since it's 1 mole gas, so Qn is equal to simply 1. CV is 5 by 2R, and delta T is heat is raised from 300 to 400 Kelvin. So 400 minus 300. So delta Q is so R is simply 8.314, the ideal gas constant, 8.314, and 100 into multiplied by 100. So this gives the answer in terms of joule. So if you multiply the three terms, this gives you 2078.5 joule. Now, so this gives you the heat that is required to raise the temperature at constant volume, right? Next thing is the next problem. It has been asked what is the heat required for the case of constant pressure, right? For constant pressure, delta Q is and Cp delta T, right? So Cp, so how could you get Cp? Okay. So in the question, it's mentioned that the gas is ideal, right? Ideal diatomic gas. So that means Cp minus Cv is equal to R, right? So that means Cp, okay, so if you know Cv, 5 by 2R equal to R, so Cp would be gives you 7 by 2R, right? This is the expression of Cp. So now if you substitute Cp here into the expression of delta Q, so delta Q gives you N into Cp is 7 by 2 into 8.314 into 100. So delta Q gives you 29.099 into 100. That is basically delta Q gives us 2909.9 joule. Okay. So this is how you can calculate. Okay. So basically in this problem, what we have done, so the problem is the for 1 mole of diatomic gas, it is heated from 300 to 400 Kelvin. So first thing is that you have to calculate the heat required at constant volume. That is, as long as CV is given, so that is pretty much straightforward. Just use this formula. This formula actually comes from here actually. So we know dq by dt at constant volume is CV, right? So you can write dq or ncv, whatever, dq as ncv dt, and if you do the integration, it gives you delta q equal to ncv delta t. Okay, so from here there we can use this formula. Okay, delta t, we know the temperature that has been raised, cv the given, n is 1 mole, that gives a delta q as this 2078.5 joule. Now, since you got the CV value, from there you can get the value of Cp, which is 7 by 2R. So substitute the Cp here. After doing that, the R is 8.314, that is the ideal gas constant, and temperature, the raised temperature is 100 Kelvin. So all the things are substitute here into the expression of delta Q, and you'll be getting the delta Q as 2909.92. That is the heat required at constant pressure, right? So that's it. So today discussion. So previously discussed about different partition function, the vibrational, rotational, translational cases. We have started from the rotational part. The rotational, like for linear case, for non-linear cases. If you raise the temperature high, what will happen to the partition function, right? All the cases we have discussed. Then comes the vibrational part. So vibrational part also same way we have discussed for both the limiting temperatures high and low. And lastly we have discussed about the electronic partition function. So here we discuss about the electronic contribution. So basically the thing is, like the electronics energy separations are very high, this delta is very high. So the mostly the system remains at the ground state. The ground degeneracy is the only contribution that fits in the partition function. Okay, from the electronic part. So if you raise the temperature very high, maybe the first excited states comes into the picture. Otherwise, the ground state is the only state that consists into the electronic partition function. So now, after getting all the partition functions, so you get the total partition function, that is Q here, and we basically got the whole expression of Q, like this is the expression of Q. Now we got the mean energy, okay, total mean energy. So total mean energy means you have to consider the translational mean energy, rotational mean energy, translational, vibrational, and electronic. So we have calculated all of the cases, like how the mean rotational or vibrational or electronic energy looks like, what is that expression at high temperature, low temperature. So all of the things you have calculated. And last we have discussed about the heat capacity, right? The heat capacity is, this is the expression that at constant volume, CV. So if you know the internal energy or the mean energy of the systems, so basically if you told the total mean energy, you can calculate the total heat capacity of that system. Or you can do, if you know the translational part, you can calculate the translational heat capacity of the systems. For the ideal gas case, if you know the CV, from there you can calculate the CP also. And based upon that, we have discussed some problems also. So so that's it for today's class. Okay, so let me just okay. So today's class, let me just stop the meeting here.